we're going to be talking about strength of intermolecular forces and also how the strength of the intermolecular forces in a sample relates to properties of the liquid, for example, boiling point, heat of vaporization. We've talked about the different intermolecular forces, and that's summarized here. This is table 10.5 from your textbook, which compares the different intermolecular forces not only in strength, but also in characteristics. Now, we've discussed most of these characteristics already, but you can return to this table as often as you wish. We're going to talk a little bit about the strength today, and we're going to go through each one, starting with ion-ion interactions. These are definitely the strongest of the intermolecular forces. The strength increases as the charges of the ions increases. So this is, for example, magnesium is a +2 charge compared to sodium, which is a +1 charge. So magnesium, having a higher charge, will exhibit stronger ion-ion forces with chloride than sodium would. This is related to Coulomb's law. The Q in the numerator, Q1, is one of the ions, and Q2 is the other ion. So Coulomb's law is related to the electrostatic force between two charges. So as the magnitude of those charges goes up, the force increases. And that probably makes sense to you conceptually as well. A higher charge will be more attracted to the other ion than a lower charge would be. Now, also in Coulomb's law is that R squared in the denominator. That is the distance between the two ions, and that is the other important factor in strength of an ion-ion interaction. The strength will increase as the distance between the two ions decreases, and what that means is that smaller ions will have stronger ion-ion interactions because they can just get closer to the other ions. So, for example, potassium is a much larger ion than sodium. It has an extra valence shell, and sodium is smaller, therefore it can get closer to chloride, which means that sodium chloride will have stronger ion-ion interactions than potassium chloride would. And I chose the cation just for fun. I could have picked the anion. For example, a -2 anion will have stronger ion-ion forces than a -1 anion. And a smaller anion, for example, fluoride, will have a stronger ion-ion interactions than chloride. So sodium fluoride will be held together more tightly than sodium chloride. Dipole-dipole interactions are relatively weak compared to the others. The strength increases as the polarity of the molecules increases. This is a table from your textbook, which has dipole moment in the middle column, which is a measure of polarity. And you can see that as the dipole moment, that number increases from 0.08 down to 3.93 at the bottom, the intermolecular forces increase. And so the 0.08 dipole moment represents a relatively nonpolar molecule with the weakest intermolecular forces, and the strongest intermolecular forces are at the bottom with the more polar molecule. Hydrogen bonding is related to how many hydrogen bonds can form. Now, this is moderate in strength compared to other intermolecular forces, so it's not as strong as ion-ion, but it is stronger than a standard dipole-dipole interaction. The strength depends on the number of hydrogen bonds that are possible, and so water is unusually strong because, as we discussed before, a water molecule has two hydrogens connected to oxygen, which means it has two hydrogen bond donors, and it also has two lone pairs on the oxygen, which means it also has two hydrogen bond acceptors, which means each water molecule can donate to and accept to, which means it can maximize its hydrogen bonding, which means that a sample of water has unusually strong intermolecular forces and therefore an unusually high boiling point, unusually high heat of vaporization, heat of fusion, all the properties that go along with strong intermolecular forces. London dispersion forces are, remember, the forces that exist between all molecules, including nonpolar molecules, and these are relatively weak. The strength depends very dramatically on the size of the molecule, and so size is related to an idea called polarizability, which is an interesting word. But if you think about these London dispersion forces come about because the electrons move around. So the easier the electrons are to move, then the stronger the London dispersion forces will be. So large molecules, large atoms, those electrons are much further from the nucleus, which means that they're much easier to move around. They're more, quote, polarizable. And so For example, if we compare the halogens, we have fluorine, chlorine, bromine, and iodine, which are all nonpolar molecules. Fluorine has by far the weakest intermolecular forces because it is the smallest, and iodine has the strongest intermolecular forces because it is so large. Now, this is also in our table here. So strength depends on size. You can see that at the bottom under London dispersion forces, and that goes along with this idea of polarizability. I want to show you that with each of these molecules, you have the model and you have the structural formula shown with it, with the atoms and how they're connected. And then underneath that is the name. And then in parentheses next to the name is the boiling point. Now the reason they're giving you the boiling point is because they're trying to show you that pentane, having stronger intermolecular forces, has a higher boiling point than 2,2-dimethylpropane because it has weaker intermolecular forces. And so that just is meant as an example the effect that these intermolecular forces have on the properties of the liquid. So strong intermolecular forces, whenever that's true, the molecules are more difficult to separate from other molecules. And that's important because as we convert something from a liquid to a gas, for example, that's what we're doing is we're separating the molecules. So the more difficult that is, the harder it's going to be to do and the higher the temperature we need to reach. Weak intermolecular forces means the molecules are very easy to separate from other molecules. And so you won't need as high a temperature to boil it, for example. Now, this is a picture that I wanted to talk a little bit more about because it shows a couple of interesting features, and so I wanted to talk about what this graph is telling us. We're going to start by looking at the group on the left, group 4A. So the boiling point of these four molecules increases as you go from CH4 to SNH4. An important point here is that these four molecules are all nonpolar. And what's important about that is that that means that the only intermolecular force present is London dispersion forces. So this increase in boiling point goes along with an increase in size or molecular weight. Because as molecular weight goes up, the strength of London dispersion forces goes up, and therefore the boiling point goes up because those molecules are held more tightly together. Now, if we look at the other three groups, then what you should first take note of is that in each group, the second, third, and fourth members of those groups all have the same trend as group 4A, right? They increase in boiling point as the size goes up, but each group also has an outlier. You can see that here. Ammonia is the outlier in group 5, water is the outlier in group 6, and hydrogen fluoride is the outlier in group 7. So we also need to talk about why that's true. Now, this first trend in the second, third, and fourth molecule in each set follows the same size trend. We already talked about that. Now, if we talk about the outliers, ammonia, water, and hydrogen fluoride have unusually high boiling points compared to other members of their same groups. And that's the other take-home message here. Why is that true? So that's the last thing we want to talk about here. We have ammonia, we have hydrogen fluoride, and we have our water models. And you can see that each of them has an attached hydrogen, and being fluorine, oxygen, or nitrogen, that of course means that they can hydrogen bond. They also each have at least one lone pair on the central atom, which means that they can accept hydrogen bonds. So we can draw those hydrogen bonds in as well. You can see here ammonia hydrogen bonding with another ammonia, water hydrogen bonding with another water molecule, and then hydrogen fluoride hydrogen bonding with another hydrogen fluoride molecule. So the ability to hydrogen bond dramatically increases the boiling point because the intermolecular forces are much, much stronger for these molecules. So we go back and just summarize what this graph is telling us. There are two important take-home messages. This is the rest of the image from the book that just describes that the boiling points increase with molecular weight down a group on the periodic table, but the hydrides of nitrogen, oxygen, and fluorine have unusually high boiling points because they can hydrogen bond. So our two take-home messages are that molecules that can hydrogen bond have higher boiling points, and that London dispersion forces increase with size. Now this is a table that we've already seen when we were talking about polarity and the strength of dipole-dipole interactions. The dipole moment, remember, is a measure of polarity, and so you can see that the molecule on the top has a very low dipole moment, meaning it is not very polar, and it has a much lower boiling point than the other two. And the molecule at the bottom has the highest dipole moment. It is the most polar of those three molecules, and it has the boiling point, the highest boiling point, because it has the strongest intermolecular forces of these three. So the take-home messages here are that more polar molecules have stronger dipole-dipole forces, and that gives them higher boiling points. One more table is a table comparing the melting points and boiling points of the halogens, which we've also already talked about. Halogens, fluorine, chlorine, bromine, and iodine, are all nonpolar molecules, which means London dispersion force is the only intermolecular forces present. And this table is showing us that larger molecules have stronger London dispersion forces, that would be iodine, which gives them higher boiling points and higher melting points. If we compare these four molecules models, you can see them here. You can also generally use a standard state of matter as a measure of the strength of the intermolecular forces present in a sample. So what I mean by that is that when you look at the bottom three halogens, chlorine, bromine, and iodine, this may be something that you already know, or maybe you don't know, and now you're going to learn it, and that is that chlorine is a gas at room temperature and room pressure. So you can see that it's kind of a greenish, yellowish green gas that's in that top flask. Bromine, however, is a liquid at room temperature. It's kind of a dark orangey brown liquid. It easily volatilizes, though. It easily evaporates, and so you can see some of the gas present. But you can see the small pool of liquid. So the liquid is the most stable state for bromine at room temperature and atmospheric pressure. And iodine, of course, is a solid at room temperature and pressure. Iodine is one of the molecules that you separated first semester when you sublimed it, and then you collected the solid deposit, the deposits of solid on the top of that watch glass. It was part of that mixture that you separated. So iodine has such strong intermolecular forces that it is actually a solid at room temperature and pressure. Chlorine and also fluorine. Fluorine isn't in our picture, but fluorine is also a gas at room temperature because it has such weak intermolecular forces because the molecules are so small.